So here we go, my magnetic induction tutorial. One of the things I wrote here is questions that I like. This is some of the stuff I might consider fair game for the written section. Multiple choice questions that I like. Almost anything from the review, you'll see some kind of variation in the multiple choice there. But written questions, looking at the induction review. You know what? I'm actually going to look at my answer key because then I can actually see the work involved as well, because that way I don't pick a back EMF that's too easy. Certainly, you know what? Something like number 3 is going to be a written. I'm going to give you a transformer. I'm going to give you something on the secondary or on the primary. I'll give you 2 things on the secondary and the primary, and then I'm either going to ask you to find the number of coils on the secondary, number of coils on the primary, voltage on the secondary, voltage on the primary, current on the secondary, current on the primary. It'll be a part A and a part B. So it's going to be find everything that's missing on a transformer. It's cross-multiplying. Please remember that for current, things are reversed. Okay? Hopefully, that'll be a fairly straightforward 6 marks or 7 marks. I think I probably made it worth 6 instead of 7 because it's kind of wishy-washy in my mind. So something like that as a written. Something like number 5 would be fair game. There's going to be some using Faraday's Law. I may give you a Faraday's Law question, Diana, like on the quiz, where one of the flux final or initial is 0, because that's a lot easier. Or I may have one like this where we reversed a direction and we had to let one way be positive and one way be negative. I'm fine either way. Okay. If, you know what, I'll even say this. If I gave you where the flux of one of them was 0 to make it easier, then I would probably make that worth 5 marks. And then for 2 marks, I might give you a resistance. And now that you have a voltage, I might say, hey, find a current. Or I might say, if the current flowing through the wire is blah, 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 hey, find the resistance. Or I ask you to do something with that voltage. That might be a nice little twist. By the way, why do we say average EMF? Because the voltage does change as it goes from full to none, to full, to that's why we have an alternating sine wave current, for those of you who are wondering. You don't need to know that, but the nerd within me just couldn't let it go. Apparently, oh yeah, number 7, I think the question didn't copy properly. Did it? There's no answers? Oh. And part of the words got chopped off, yes? Okay, sorry. In fact, I think number 7 is actually number 5 that somehow I need to nuke. Anyways, so, 8 would be a good multiple choice. I think that's a little challenging as a written. Those are multiple choice. I mean, 14, make that a written. Right, I'm asking you to find 2 things. Primary current, secondary voltage. There, that's a transformer question. I like number 15. So number 15, I'm asking you how many windings a solenoid have. I'm asking you to use a solenoid equation from last year. That's totally fair game. And then asking you to do something with it here as a flux. In other words, I would have no problem, instead of just giving you numbers, something with the magnetic field. Dorothy, I'd like you to do something with a solenoid. I think you can expect that somehow. Or another option would be give you a big solenoid, move a conducting rod through it at a speed so that you want to use BLV, but I haven't told you B. Oh, I've put it inside a solenoid. Calculate B, please. That would be another nice one to say. I'll see what else I come across here. So number 17, absolutely, but make this a written question. So here is where I didn't tell you the resistance. You need to notice that when we're not turning, the back EMF is 0, and I can find the internal resistance, and then now I can find the back voltage at speed. Okay? '18's cool, but a little overkill, I think. Oh, here. Here's a good example of a transformer's written question, right? On multiple choice, you can definitely expect something like number 22, a Lenz's law question, where I say to you, all right, what direction is the induced current or the induced magnetic field? How do you figure it out? Ask yourself, what's the magnetic field causing the current in the first place? The created or induced current will create a magnetic field that opposes that one. So if it's a north pole moving to the left, it's going to create a north pole pointing to the right. If it's a north pole moving away, it's going to create a south pole pulling towards, or in this case, this is the copper pipe demo that I did with you, where we dropped the magnets down the copper pipe, which was very cool. Yeah, it's a right-hand rule question. I was like, what are you doing, waving at a oh, right-hand rule. Yeah, so, I mean, here, this, to me, this was actually a written question for 7 marks. To me, this was too easy. Now, I think the rest of the provincial that year was compensated by being a little bit tougher. This was the easy written question, because this page is about straight as plug and chug as you get. You need the change in flux. Oh, hey, one of them is 0. Oh, and it's not even circle. It's a rectangle. The area is, you don't have to go pi r squared. It's just length times width, for Pete's sakes. But, probably one of those. Definitely multiple choice, maybe a written. Sure, asking you to use this equation, but giving you the other variables and saying, oh, find T or find N, or if it's a change in flux, find the magnetic field or the area. If I do that, though, one of the fluxes will be 0 to make the equation a little cleaner, Dorothy, okay? So like this one here, what's the strength? I gave you the flux in Webers and the radius of the, okay, what's the strength of the magnetic field? Flux is going to be B times A. B is flux divided by A, flux divided by pi r squared. Remember, flux is in Webers. Transformer again, sure. Yeah, he has a unit named after him. So here, this will be the type of back EMF question I'm going to give you again. So unlike the quiz, which was just all plug and chug, this one here, oh, they didn't tell me the radius, the resistance. I'm going to have to calculate the resistance, little r. How? I know, Alejandro, that when the motor is prevented from turning, what's the back voltage? What's the back EMF if I don't let it turn? 0. I won't tell you that, but that's why I can put a 0 in the equation right here. Equals full EMF minus I times R. And then once you have the resistance, that's not going to change. Once you're at speed, the resistance of the motor isn't going to change. The current flowing through it will. The back EMF will. Oh, let's go find some of those, depending on what I give you. Oh, this was kind of cool as a graph. So this was a graph of voltage divided by current. What is voltage divided by current? It's got to be the resistance. The resistance of the motor, I think, the actual armature. Right? We're using slope. Yeah, there is a graph to interpret on this test. I think it's a multiple choice question, but there is some kind of a graph to interpret on this test. Oh, yeah, so here's what I was saying as an example of, here's where we're using BLV, which is way too easy. Oh, but wait a minute, I made you use a solenoid to try and find the magnetic field before you could go BLV. I think that would be a much better written combination question, a two-parter, as opposed to just, because otherwise BLV is just plug and chug, too easy. Pardon me? I would have no problem if you remove, this would make a good written question in my mind, because it's got 2 parts. What I'm saying is, in this unit, Dorothy, so many of the equations have just been type-in stuff. You know what? That's a little wishy-washy for written. I need a 2-parter somehow, or find one of the missing pieces of data, right? Another way is, if I gave you this equation, the BLV, and I said find the velocity, but instead of giving you the voltage, maybe I gave you a small circuit, and you knew the current, and you knew the resistance, and you had to find the voltage, and then go from there. Okay, I think that would be a little more Physics 12-ish, if that's a verb or adjective. 31 again, same idea. This was, 34 was a bit different. They wanted the change in magnetic field strength. Well, I'd never seen this question before, but Emily, what's change in anything? So I said, I guess they want me to find change in final. You know what? I said, I wrote this down, then I said, now change in flux is, you can also think of it as area times change in magnetic field. What we had been doing was actually changing the area, going from full to 0. So I said, okay, I'll get the delta B by itself, I guess. That's a little weird. I don't think I like that. I like that question as a nerd. I don't think I like that question in terms of assessment. Okay.
So sorry.
Sure. Kenzie, can you put it face down on top of block D for me, please? Oh, and they brought food. I totally care. Here we go. Sure. 36 I like. 38 I like. Sure, 42, again, find the resistance first, knowing that the back EMF is 0, and then find the back EMF. So 42 is what you'll see on the test. Different numbers, obviously. Oh, that's straight plug and chug, multiple choice. By the way, why is the answer in number 45 A and not B? Yeah, in fact, B, you won't get anything. Unless you add a switch and flick it off and on, flick it off and on, flick it off and on. Direct current, you're not changing the flux. And remember, it's not magnetic field that causes current. This is why Faraday was so brilliant. Up until then, everyone figured, oh, magnetic fields don't cause current. They don't. He realized changing magnetic field. He was the great experimentalist. He noticed, my needle did move for a split second. Why? 46 is kind of cool, but a little tricky. Scholarship, 10. I would expect you to understand the explanation. You can't do 48, but now you recognize some of it. 48 is actually a torque question. You know how I know? There's a beam right here, balancing. You technically can now, but it's a little bit of a yucky one, but there's torques there. Yay. 49A I thought was pretty fine. A little tricky, but not too bad. So those are the questions that I liked. I said a lot. Paige, what were the ones that I said I liked? You wrote them down, yeah?
Yeah.
3.
5.
Keep going.
8. 14. 15. 17. 19. 22. 23. 24. 26. 28. 29. 30. 31. 36. 38. 42. 44. 45. 46. And 49A.
But you're going to notice in that batch, there's really only 4 different types of questions. I think 6 of them were transformers, for Pete's sakes. It's a short unit. But cool, I find this stuff very, this is the foundations of all of our electric infrastructure. That's what those silly barrels are sitting on the telephone poles. Kind of wondered. Now I know. So having said that then, any of those you want me to go over? Any questions from the review that you want me to go over? I don't know if I'm going to reteach stuff per se, because it's only been 5 lessons really, and 2 of them were kind of pluggy and chuggish. Any from the review that you want me to go over that you're going, Mr. Dueck, I have no idea how the heck you got that answer. Now is your chance to ask. Some of the direction ones maybe you might want to ask if you want. Show, which one?
27, just like the
Number 27. Thought you were leaving already, and I was going to say, really? Are you leaving already? Really? I'm sure you will. 27. Magnitude and direction of the current. Okay, so let's go like this. Clip this first of all. Scroll down, get the rest of the question. So was your question about the direction or the magnitude or both?
more of the direction.
Okay. So the direction, and this is going to be tough for those of you at home online. This is a Lenz's law question. I see a before and after. Do you? Stay with me. Just don't turn for a second. Put yourself, relax. See the after? See the external magnetic field that's causing the current is coming out of the page towards me. Okay? That means that nature is going to create a magnetic field opposing that. What would oppose a magnetic field out of the page? What's the opposite of a magnetic field out of the page? The coil, which is up here, is going to create a magnetic field into the page. So with my right hand, sorry for those of you watching at home, with my right thumb, I'm going to point it into this page. Up here in this coil section, the current show is going to go this way. I'm going to add arrows and then follow it all the way through. Okay? I don't know yet. I'm going to add arrows. I know it has to be the opposite magnetic field because Lenz's law kicks in. By the way, if it didn't, then that would create a stronger magnetic field, which would create a stronger current, which would create a stronger magnetic field, which would you'd be getting free energy. That's why the universe does. They don't get free energy. Really, you could argue that Lenz's law falls out of conservation of energy. You get nothing for free. See it? See it? You know what? What's the direction through this resistor? From X to Y show or from Y to X? Okay, so I would go no, yes, no, yes. Then we need to get the magnitude of the current in the interest of time. Okay. To get the current, I wrote, well, they gave me a resistance. I need V over R. Oh, V voltage. You know what? I need an EMF because this is going to be, I see we have a changing magnetic field. This is Faraday's law. This is the negative N, change in flux over change in time. Ooh, I got to be careful though, because what direction was my initial magnetic field? Into the page. What direction is my final magnetic field? I better let one of those be positive and one of those be negative. This is not like where we went from flux to zero. This is, you know what, they flipped the magnetic field around. So it looks like I let the final magnetic field be negative and the initial be positive because I stuck a negative right here. Flux times area, magnetic field times area, magnetic field times area. I got a negative there, plugged it in. I did get a negative answer. The negative is just a directional convention because down isn't necessarily positive and up isn't necessarily negative when a magnetic field. So I ditched the negative in my final answer. I just said, you know what? The voltage that I'm going to generate here, the average voltage is 0.78 volts. Divided by the resistance, the average current is going to be 0.052 amps. Is that all right? Did I answer your direction question okay?
Yeah.
Okay. Next. Any others from the review, from the homework, from wherever? I thought someone had one.
30.
Did you try it?
No.
Yeah.
Sorry.
Okay, I'll do it with you because I'm nice. Lazy punk. Won't miss you. What do they want me to find?
EMF.
EMF, and I see a conducting rod. You know what? The first thing that I think to myself is, I'm probably going to use this. So I double checked. I said, did they give me the speed? Yay! Did they give me the length of the solenoid? Yay! Sorry, of the rod? Yay! Got to be careful. There's lots of lengths, but I said I want the length of the rod that's moving. Did they give me the magnetic field? Teslas. No! So you'll see my answer key I wrote. Well, what's causing the magnetic field? The solenoid. That it's inside. Okay. The magnetic field of a solenoid is what? It's on your formula sheet somewhere. Mu naught, the permeability of free space. What? Capital N I over L, yes?
Yeah.
So let's see. This is 4 pi times 10 to the negative 7. N. Oh, 4,700, yes? I. Okay, I got to be careful. Sometimes to really mess people up, they'll give people the current in here too, so that they have two currents to pick from. I want the current of the wires in the solenoid, which is 25, divided by, there are two lengths. Which length do I want? The length of the solenoid, because that's what's affecting the magnetic field. So I want the... and they even tried to really gum me up by giving me a radius. They're really trying to tempt me. In fact, I'm sure one of these is if you use that, or you do some kind of an area thing, or maybe I can do this with an area. I don't know, but I'm going to use BLV, because I did say to you guys, Faraday's law can morph into BLV, which can morph into N, change in flux over change in time, if you're clever. What was L? 0.75? So that's going to give me the magnetic field, and then the baud, I'll truck that over to there.
Would you use 0.1?
Would I use 0.1 for the... yeah, I would use this is going to be the length of the actual bar, which is going to be 0.1, and the velocity of the conducting rod. If I wanted to go a little nasty, if you knew the direction of the magnetic field from the solenoid, you could figure out which end of the bar is positive, which end of the bar is negative. Supposing, I'm just making this up, supposing the magnetic field was coming out of the page towards me. Which way is the bar moving? Which way is the conducting rod moving? To the right. So I point my thumb to the right. Magnetic field is coming out of the page towards me. What part of the bar would be positive? The bottom. What part of the bar would be negative? The top. Because there's an arrow on it.
Oh. Okay.
As I said, some more than others. We're looking at a little, this is made up of a whole bunch of positive charges holding hands. We focus on just the little guy standing in the middle there. Which way is he moving? Which way is his velocity? That's why you point, that's which way the positive charges are moving. Which way is the magnetic field? Out of the page towards me, right? The positives would get pushed to the bottom of this rod. The negatives would get pushed to the top. That's what we said in lesson 1 of this unit. You're inducing a voltage. You're doing work because you're separating charges. That's why you feel when you turn that crank. That's the force that you feel resisting you. You're actually separating. You're doing physical work. You're separating charges. Storing energy. That energy can be used for something. You hook it up to a circuit. Is that okay? Yeah. Okay. By the way, we never pointed our thumb in the direction of the magnetic field.
That's this one.
The magnetic field is fingers, yes. I wonder if there was some easy way that I can remember that field was fingers. Field was fingers. I got nothing. I wonder if there was some bilingual French way that I can remember that my man was the magnetic field. Mes mains was the magnetic field. You know, it would be convenient. I got nothing. I wonder... Okay, I flogged it to death. I got nothing in Japanese. If I was good, if I was really good, I would have come up with something then too, you know. Well, I've done my research and... Okay. Is that all right?
Yeah.
If the magnetic field was going... Let me erase this, by the way, because that wasn't part of the question, and when kids look at that, they'll freak out. If the magnetic field was going the other way... by the way, how could I figure out that direction? If you had told me which way the current was going through these wires, I could actually use my solenoid rule. If it was going this way, then the magnetic field would be coming out of the page towards me. If the current was going that way, magnetic field would be going into the page. That would be a terrific question. If I could do those graphics, I would totally throw that on the test. I can't. Although I may, like, it would take me about probably 4 hours to set up a question like that, so that I can make it nice and clear. And
It's like you're 10.
well, but you've seen my drawing and my art. I am at least partly embarrassed by that sometimes. So I may swallow my pride and redo all my tests this year in pen and just live with it, because I have a feeling some of my tests might be out there. I don't know. Any others? Any other questions you want me to go over? Otherwise, this will be a fairly short tutorial, which is also okay. Maybe you were all just here for the hints. Yeah.
Number 4.
Number 4, love to. And then Sebastian, you had one as well?
I just like about like how many like
graph question.
Oh, the graph one?
Yeah.
Okay. I'll come back to that. Number 4. Whoop, too far. Ah, this is kind of a cool one. Shrink. This was a fairly challenging one. This was a nasty, so you've asked me a good question. This, you could argue, partly overlaps last unit and partly overlaps this unit. What are they asking me to find? Force. I'm thinking my equations that have force in them. I think we had 2. We had QVB. This is not an individual charge. We had Bill, which was for a wire. You know what? This is a wire. It's an L-shaped wire, but this is a wire. I'm going to use F Bill. FB equals Bill. And what I'm going to do is I'm going to treat this as one chunk of wire and this as one chunk of wire because the current is moving that way in one section and moving that way in one section. So I'll find for this section, which is going to be 0.02, that's the magnetic field. Current 25, length 0.12. 0.06 newtons. Is that okay so far? I'm going to do the same for this section, which is going to be, it turns out to be exactly the same numbers. But here's the problem. This is force. It's a vector. I'm going to have to be adding some vectors together. First of all, I need some directions. In this bottom one, we point our thumb in the direction of the current. Point your right thumb in the direction of the current. Which way is the magnetic field fingers? Magnetic field, what do those dots mean? Coming out of the page towards us? So, oh boy, you know what? I got to stand up. That. This is going to get pushed up. How much? 0.06 newtons. What about this one? Current is up the page. Magnetic field still out of the page. You know what? It's going to get pushed to the right. And because these are attached right there, this L-shaped piece of conducting rod is going to feel both forces. 0.06 newtons. How do I add up and right? It's not 0.12. How do I add those two vectors together? Draw them. So it's going to be 0.06 plus 0.06. This is going to be a hypotenuse. It's going to be whatever that squared plus that squared equals the square root. Oh, by the way, ready? You, Chen? No? Kevin?
Yeah.
No? Yes? No, because that's one force and there's two of them, right? That's just that. No, I know I'm not supposed to just add them together because they're vectors. Without a calculator, the answer has to be C. Thank you very much. You've been a good audience. Try the veal.
Does it matter if the current is in the same direction as the length?
Pardon me?
Does it matter if the current is in the same direction as the length?
Hugely. First of all, to try and run a current this way, it can't exactly go anywhere.
Yeah.
Also, if you try then pointing your thumb that way, magnetic field out of the, it's going, so yeah, we want the current running down the wire. Yep. I mean, again, this is where all the physics that I've taught you is wrong. It is true, since we've treated all of our wires as though they have zero thickness. They don't really. So there is some small voltage separation in the wire as, well, you know what, it's zero. It's so small, forget it, right? So we have looked at questions like, here, for example, where we said, in this direction, you'll get a voltage created, but if it moves in this direction, you won't get the EMF. You may remember in lesson 1, we talked about which situation where you wouldn't get a big EMF created, a big separation of charges, because there was nowhere there to go. Well, okay, fair enough. Which one, Sebastian?
The graph question.
which was number?
29.
Okay. So what I've tried to teach you this year is a generic, handy-dandy, hey, this will always work approach to handling a graph question. Can I get this? I have to cut and paste this in a couple of chunks. On your final, and I think on this next test, I'm either going to ask you something to do with slope or area. If it's slope, what do you do with the x and the y units? Divide them, y divided by x, because it's rise over run, right? And if you can't spot it with the units, the y variable divided by the x variable, either of those will get you out of it 99% of the time. If it's area, now that those of you are in calculus, you now know this too, what do you do with the units? You multiply them. It's actually integration, but you multiply them. Or you multiply the variables. So let's look at this weird, funky one here. It's going to take me a little bit to copy it. I can do that. Scroll down. Can do that. And the last thing it wants is what property? Okay. So if it wants you to plot the data, I probably won't ask you to actually plot the data, because to me that's a waste of time. You guys have learned how to do it. I'll give you a graph that's made up already, but okay. It tells me they want voltage on the y-axis. The biggest voltage I have is 7.5. I went, 1, 2, 3, 4, 5. What should I go up by? What did I go up by in my actual solution key? Well, really? Okay, count. 5, 10, 15, 20, 25. I got 7.5. What's 7.5 divided by 25? You could go, I think, each of these 0.3 volts, which is a bit of an awkward scale. So I probably went each of these being a half a volt. Is that going to get me there? No, I went each of these, I think, 1, 2, 3, 4. I think I went like this. 2 volts, 4 volts, 6 volts, 8 volts. There, that's pretty close to using up all of 7.5. Current, it goes up to 6, and it's nice and even. I said, okay, 1, 2, 3, 4, 5, 6. Hey, there we go. That works nice. So at 0 volts, we're at 7.5, 6, 7. Oh, there's 7.5. That works out quite nice, actually. Sorry, at 0 amps, we're at 7.5 volts. At 2 amps, we're at 6 volts. So at 2 amps, we're... Am I wrong?
Not 1.
1. I'm sorry. Good gosh, Mr. Dueck. Here I am thinking that's a 0, 0. 1, we're at 7.5. Right? 2 amps, we're at 6. Is that right? I have, sorry? I'm a little low on my first one. You're right, I am, because I'm at 7 even. This is harder than it looks on a flat screen like this. This is why I don't like the electronic exams for the grade 10s. 3, 4.5, 4.5, 4.5, 3. Hey, that looks better. 4 goes through 3. 4 amps goes through 3 amps. 5 goes through 1.5. 5 goes through 1.5. Be right about there. Hey, this looks pretty good. 6 goes through 0. Hey, I can get that right as well. I would use a ruler. Now, if you're drawing a line of best fit, you want to go through as many points as you can. If some of these were a bit off, you would just split the difference. I'm going to be bad and freehand this, and that's terrible, I know. And you know what? I shouldn't go below 0.
That's actually pretty good.
Okay. Now that I've done this, by the way, if they ask you a question about slope, make sure that you use points that are on your line. I could not use that point or that point, even though I know the numbers from my chart. If I used those to calculate slope on Bridgel, they would have taken marks off. So they would have said, wait a minute, you've committed to your line of best fit, and now you're using data that's not on it. You're analyzing a line with points that...
Best fit. Oh.
Okay? In other words, well, look, did I go through it? So I can't use that to calculate slope technically, okay? Meanwhile, they said, find the slope of this graph. I said, okay, I made sure when I drew my graph that I went through this with my ruler. And then I said, I can go rise over run, because this is not, I always like to use a 0 if I can, right? I said, the slope, negative, downhill. What's the rise? I said 7.5 over. What's the run? 6? Oh, no, careful, Mr. Dueck. 5, right? From here to here. 5, not 6. And this was nice because it worked out nice and even. 7.5 divided by 5 is what?
Negative.
Okay. Units. Volts per meter, Mr. Dueck, per amp.
Zachary Hetherington, please come to the office.
So what was your question, Gabby?
Oh, was that resistance?
First and last. I try not to.
Oh, yeah.
So negative. Resistant, the reason I said it's resistance, I said, it's current, it's voltage over current, it's resistance. What's the negative? I think you're getting an absolute value here because the voltage direction is, you can be negative or positive. So I didn't freak out about the fact that we had a negative resistance. The resistance of what? I think it's the resistance of the armature of the motor. Okay. You had a question? No, you're good?
Does it matter if you put volts over amp or ohms for that one?
No, in fact, if you wrote ohms, I'd be like, woohoo! Cool, you spotted it right away. Yeah. I would have, but I didn't want to lose my students in the answer key, so volts over amps. Hey, that is voltage divided by current. It's got to be resistance. In fact, I think if this was the provincial, I think it actually wanted what slope, what property, and the units. So it would have been resistance, comma, in ohms, I think is what they wanted for full marks. Okay. So let me find a formulas page. And give you kind of an example or an idea. Formula sheet. So the equations that we've used in this unit are primarily this one,
Zach
this one,
Hetherington
this
or
one,
Miss-
this one. There's your definition of flux. This one. This one here is sort of a y equals mx plus b, where you have a negative slope and your EMF would be the y-intercept. Or if I plus this over to this side, your back voltage would be the y-intercept. That would be one way of thinking about it. This one I won't do because multiplying, these are reciprocal curvy graphs, which are a bit tricky. But let me give you, I'm just off the top of my head. If I gave you a graph of voltage over time, or flux over time, the slope could be the voltage. There's all sorts of ways to think about this, right? If I gave you a graph of voltage over magnetic field, it could be the velocity times the length left over. Or this one isn't a great one to deal with, but this one, there's lots of ways to mix and match these for a graph. And it'll be a multiple choice, I think, graph this time. On your final, and I'll be typing the final up probably this weekend. I'll give you more information about it next weekend. And I think I'm going to change it a bit. I may go 2 questions per unit, pick one. Okay. But then I might make them a little nastier, but feel a little more comfortable. So it might be open page. Here's 2 kinematics questions. Cross one out, do one. Turn the page. Here's 2 forces questions. Cross one out, do one. Turn the page. Here's 2 momentum energy questions. Cross one out, do one. I think that's what I might try. Since there is no provincial exam, I can have more fun in assessing you and be fairer.
Yeah, because you said that we weren't going to be able to write 2.
Yeah, and I'm feeling a little bit guilty about that. I mean, not hugely, because I'm willing to bet I'm also the only teacher out there that's been doing 2 or 3 or 4 final exams.
We had Mr. Cruz, actually.
Did he?
That's the only other teacher
Hey.
in 5 years.
There you go. So, we obsess over marks. Any other questions?
Are you gonna include like a step up and step down?
Absolutely. So what's a step-up transformer? What gets bigger? Secondary voltage. What gets smaller? In a step-up transformer, what gets smaller? Current. Oh, what else gets bigger? The number of coils is bigger in the secondary because that's what gives you the bigger voltage. And because V equals I times R, when V gets bigger, I does get smaller because your R hasn't changed. It also comes out of Ohm's law for what it's worth. So yeah, you know what? You can expect that as a multiple choice kind of a vocabulary. Which of the following is a step up, or one of those columns? Find the voltage. Is it step up or step down? Step up or step down? I'll have several different voltages to pick from, something like that. Okay. Yeah. So there's your hints. Any others? 18 is good. Show's been working on some of this. You guys need to thank him.
Thanks, Joe.
It's not show, it's Superman.
Superman.
Figured I may as well write the answer at least. Oh, this was kind of cool. Okay. Here's your railgun. I mean, the nerd within me loves the physics. This is really a wrapping your brain around tricky concept. And I didn't gloss over it, but this is also from last unit, but it kind of ties into this one because you do generate a back EMF and all sorts of stuff as well. It says the diagram below shows a blah, 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 blah. Find the initial acceleration. What do they want you to find? Must be a force. What's causing the force? Current and you know what? Initial acceleration, I'm going to start out saying, you know what? I think F equals Bill. MA equals Bill. Is that okay? Did they tell me the magnetic field, the external magnetic field, 0.2? Did they tell me the current going through this whole system? They did not. But what they did tell me, look up, is the resistance and the voltage. So they did tell me the current, just not blatantly. I need to realize that the current is going to be V over R. It's 15 divided by 3. Now, this is only at the start for a split second.
Hetherington, please head to the office.
Anyways, in your head, show 15 divided by 3. So 5 amps. Which length? The length of wire that it's conducting across, the 0.4, divided by, please tell me they gave me the mass of the wire. Oh, they did right at the beginning there. And initially, I get an acceleration of, a pretty spectacular one, I think, 0.2 times 5 times 0.4 divided by 0.01, 40 meters per second squared. Yes, yes, no, no, cross out, cross out. What's the maximum velocity? Maximum what? That's got a V in it, yes? What is the maximum velocity? The maximum velocity is when the net voltage is 0, when the back voltage is equal to 15 volts. Now remember, here's what we said happened. We have 2 different types of motion here. This is good right-hand rule review. Right when we turn this on, the current's going to flow this way. The current's going to be flowing up the page. Which way is the magnetic field? Up. It's going to start to accelerate. As soon as it starts to accelerate, there's a little positive charge sitting there. Not only is he moving up, he's now moving sideways to the right. So I can also point my thumb to the right. Magnetic field still up. He's going to now experience a force in the opposite direction of the battery. Okay? What's the maximum back EMF that we can generate? Because this is an induced voltage. This down here is an induced voltage. It's actually the back EMF that you're creating. What's the maximum? When it exactly cancels out this one, 15. So it's going to be 15. There's your back EMF. Magnetic field was still 0.2. L was still 0.4. Looks like 190 meters per second. No, yes. Let me double check to make sure I did that one right, but I think I did. It was number 18. That's a cool one. Railgun. By the way, 190 meters per second. That's still hauling pretty good. Right? So there you go. At maximum velocity, the back voltage is the EMF.
F equals BIL?
Yep, that's last unit.
What F is that? Is it just
Magnetic force. That's the force that a conducting wire, a current carrying wire feels when it's going perpendicularly to a magnetic field. That's the one, remember I showed you the video last unit of the jumping wire, where when he turned the switch on, the wire moved up, and then when he reversed it, the wire actually pulled the towers right in. That's that force there, except instead of a wire that's flexible, we're saying, hey, that's a wire, we just make it rigid and let it slide along these railings so that it can move forward and go shooting forwards. Okay? That's from last unit, but the back EMF portion is from this unit. So like I've said, there's a lot of overlap between the two, so anything from last unit's fair game. Kind of cool. Any others? Show you got more. They're enjoying this. You're asking questions that they would have asked had they done the homework. Just saying. But my only negative with this grade 12 group this year is the number of ultimate reviews I get handed in 3 or 4 days after the test. Show, any more?
number
Kevin, any more? Sorry?
Number 8.
Number 8. Love to. Very similar to what you just asked. Okay. Let's go Clippy Clippy. Yoink. And let's get the answers to pick from, Mr. Dueck. All right. What are the magnitude and direction of the current? Okay. Now, this time, someone else is moving it. There is no external current. You see a battery anywhere, like the previous one? So in the previous one, we supplied voltage and current to get motion. Here, someone is supplying motion to get current. Okay? Let's see if we can first of all figure out the direction of the current. We're going to do that by looking at one little positive guy right there. There's our positive charge. Which way is he traveling right now? To the left. So I'm going to point my right thumb to the left. Which way is the magnetic field? Out of the page. So it's going to go up, and it can't go this way because there's no connection. It wants to complete the circuit, so it's going to go through location X. It's going to be heading to the... Is that what it wants as an answer? I hope. I'm going to draw this in. Current, 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 current. No, yes, no, yes. Cross out, cross out. Now, apparently I copied the question twice. The question's so nice, I asked it twice. We want the magnitude. Well, as soon as I think current and magnitude, I'm usually heading towards current equals V over... I'm usually, my fallback is Ohm's law. Especially because I see an R! 5 ohms. I don't yet have a voltage. Sorry? Darn right we can use E equals BLV. Did they give me the magnetic field in Teslas? Check. Did they give me the length of the rod? I'm not going to use 0.75. I'm going to use 0.4 because that's the section that is undergoing this force. Did they give me the velocity? 8. So I'm going to use BLV over R. The current is going to be 0.25. Really, the trickiest part is picking the right L. 0.4, because 8, how many meters per second are there in the question? Divided by 5. And that should give you the 0.16. Is the answer B? I hope it is. This is number 8.
Yeah.
Yep. Nope, wrong one. That one, no. And again, I didn't really need to crunch the numbers. I could have just said, you know what? This length would give me a bigger answer. This length would give me a smaller answer. I'm using the smaller length. Pick the smaller answer. I would have typed it in, but if I was in a rush, there's I can cut corners. I used to spend more time showing these tricks back when there was a 2-hour provincial, because if I could save you 15 minutes on that provincial, that was gold. Oh, any trick of the trade I can give you, I'll do that. That gave you 15 minutes to make a mistake and recover, or for your mind to wander and have that moment instead of rushing the whole way through. But as is, with no provincial, I'm not going to freak out. Any others? Dorothy's looking back at show with hope in her eyes. Did you have any more? Don't feel bad. They're loving this.
Okay, number 9.
Number 9? Okay. Good question. This is going to be a Lenz's law question, and I think it's going to be a Lenz's law question more than once. Let's see. Nope, I don't want that. I want this. So it says a bar magnet is moving toward a solenoid. In my mind, I would underline that. Oh, which pole is moving toward the solenoid? Okay, its south pole is moving towards it. There is a changing magnetic field strength because we're getting closer, so there's a changing flux. So we will induce a current in this solenoid. Even though there's no battery, we will actually be able to measure a current with this galvanometer right there. What direction, how big? Let's figure that out. What pole is moving to the right? The current that's created here will create a magnetic field such that it resists, it opposes the magnetic field that's causing it. What would oppose a south pole moving to the right? It's going to put a south pole right there. Oh, and by default, a north pole right there. Good. All of you pointed your thumbs to the right because now you're saying, hey, which way is the current moving? I think my fingers are curling over the top towards me. Yes? So I'll draw that in. Over the top towards me, over the top towards me. Oh, follow it, follow it, follow it, follow it. Yes, yes, no, no. Now, which way is the direction of the magnetic field at location P? Outside, the magnetic field line is going to go like this. But because magnetic field lines have no beginning and no ending, in fact, really, the solenoid rule that I've given you tells you the direction of the magnetic field inside the solenoid. It also tells you which end of the solenoid is north, but that continues inside as well. The magnetic field inside the solenoid is pointing to the right. Above on the outside, it's pointing to the left. Below on the outside, it'd be pointing to the left down, but inside, it's pointing to the right. Yes, no, cross out, cross out, cross out, woohoo. Keep going, show. Keep going. Is that okay?
Yeah.
Yep. We'll go till 4, so you get 7 more minutes to ask away. Unless you run out, and that's also equally fine by me. Over under on whether there's another paging for our student that's been paged 3 times?
So Lenz's law is like the thing where like
Lenses is an English rule, not an equation.
Yeah, he's the guy who says like there's no energy.
No free energy.
Yeah.
So really, on your test, going to be two situations. I'm either going to give you a side view like this, in which case you ask, what's the closest pole towards the device I'm asking you about, and which way is it moving? Put a pole resisting that. Or I may give you a vertical view, same idea. Or I'm going to give you that before and after, like the very first question you asked me about direction a few minutes ago. Look at the final magnetic field. Which way is it pointing? It's going to be into the page or out of the page. Point your thumb in the opposite direction. That's which way the new magnetic field is being created. Lenz's law. And don't feel bad, show. This is one my ESL students in particular have trouble with because it's the first rule I've given you. It's not an equation. I mean, Newton's laws are sort of not equations, but those you can wrap your brain around. This is just, hey, here's this weird phenomenon. How can we explain it? Nothing for free. Except your mother's love. Most of you. What was that?
So it's like scoring in your paint, it's never easy.
Yeah. Well, if you're playing Garibaldi, it's not that tough. Speaking of, should be a good game tonight. Boy, if they lose,
If they lose, I take easy
Not
at 85.
3, not 4, only 1, fellas. Your little boast 3 years ago.
Well, how many they went? He started counting past the contract he signed.
So let's find one where the direction really matters here. I have one in mind. Let me go spot it. Let me scroll really, really fast. I know the one I have in mind. I think. With my luck, it was like number 1 or number 2. I'm sure I have one in mind. Oh, sure, something like number 40. Okay. Well, this is a changing flux question. What two directions would change the flux? Can you see if you move it up and down, you're not going to change the flux. You have to move it left or right. But I can also answer it in terms of your question as well, because if I move this bar here up the page, magnetic field into the page, this is perpendicular. It will induce an EMF pushing positives that way. But at the bottom, it will push positives that way. When you push positives toward, it's not going to go anywhere because they're not going to want to run into each other. Okay? If I moved this guy straight up the page, point my fingers this way, magnetic field, all it can do is get pushed a tiny bit to the left. You know what? You can't separate the charges there. So this would be, imagine me giving you 4 different bars with different orientations and saying, hey, which is one's going to give you the biggest EMF? It's going to be do your right-hand rule on all of them. And again, what I've tried to teach you, show you strategy is put a little positive right in the middle and ask which way is he going to get moved. And he's got to be separated from the negatives for you to generate a voltage. I thought I had one like that on there. Of course, I didn't look at page 1 or 2. Money. Oh, yeah, sure. Which side is positively charged here? X or Y? Put a positive right there, moving to the right, magnetic field out of the page. But you're not going to get a positive charge there or there. I thought I had one. Maybe I'm thinking of... Maybe I'm thinking this. Oh, that's my answer key. Let me find the actual blank one. Here you go. This is the one I was remembering. It says the wire shown above moves through a magnetic field. In which of the following directions would it move for the EMF generated between its ends to be the greatest? North, well, if I move up, again, we imagine a little positive charge right there, magnetic field into the page. You know what? You're going to separate the charges, but not by much. No. East, let's see, move that way, magnetic field into the page, right? Oh, the positives are going to get pushed up, the negatives are going to get pushed down, and there's some distance of separation between them. Ooh, now you're doing work. Now you've created technically a battery. So it's B, east. Is that okay? I may add that to my review next year. Well, this is so badly done diagrams, though. Any others? Okay, then we are going to wrap it up. I didn't even give Show a chance to respond. I'm going to hit